deep dive. And yeah, a really special welcome today to all of Mr. Chi's students and followers tuning in.
Absolutely. We know exam time is closing in.
For sure. So look, our mission today is basically to give you the ultimate study session, maybe even a shortcut, for that natural sciences pre-exam. This isn't just reading through it. We want this to be like an intellectual toolkit. We want everyone, whether you feel like you need a bit more foundation or if you're one of the high flyers aiming for top marks.
Everyone gets something valuable. Maximum insight. That's the goal.
Exactly.
So we're taking that grade 8 pre-exam paper and the memo too, and we're really going to dissect it. We're not just giving answers.
No way.
We're digging into the why, looking at the science behind every single answer, trying to bridge that gap, between just knowing a fact and actually understanding how it works.
Yeah, understanding the mechanics. So we're hitting two massive areas. First up, it's all about energy and change. That means electricity, light, all that dynamic stuff. And then we shift gears completely. We go huge, looking at Earth and beyond. That's the astronomy section. It's pretty humbling stuff.
It really is. So yeah, a lot to cover.
Think of this maybe as connecting the dots for you.
That's a good way to put it. We'll start with those, let's say, low-order questions, the definitions, the quick facts you got to memorize.
Okay.
But then immediately we'll pivot. We'll connect those facts to the bigger picture, the middle and high-order thinking, the principles that explain why they're true.
So you don't just pass, you actually leave feeling like you get it.
That's the aim, deep understanding.
All right. So everyone listening, grab your notes, get ready, and seriously, pause this, rewind it whenever you need. If something sounds complex, just take a moment.
Let those aha moments happen.
Let's make these concepts click, not just stick.
Yeah.
Okay, ready? Section A, energy and change. Okay, question 1 kicks off with 3 multiple choice questions. Pretty standard start, testing those core ideas.
Yeah, and these are important, like foundational checks. You need this basic vocabulary, this baseline understanding to even talk about the more complex physics later on. Can't build without a foundation.
Right. So Q1.1 asks for an example of an electric spark. Options are there, but the answer is C, lightning. Why is lightning the, perfect example here?
Well, lightning is just electrostatics on a massive dramatic scale.
Yeah.
You get this huge buildup of static charge, either inside a cloud or between the cloud and the ground.
Okay.
And this difference in charge, this potential difference, it gets so big, the electrical tension, you could say, it becomes too much for the air, which normally acts as an insulator.
The air can't hold it back anymore.
Exactly. The air breaks down, and suddenly all that built-up charge flows violently.
Yeah.
That flow is the massive spark we see as lightning. It's a rapid equalization, pure electrostatics in action, just huge.
Wow, okay. Moving to Q1.2, this one's about measurement.
Okay.
Which instrument measures the flow of charge, the current in a circuit? The answer is B, the ammeter.
Yeah, and this is a classic spot where students get tripped up sometimes. They mix it up with the voltmeter.
Right, why isn't it a voltmeter?
Okay, so a voltmeter measures potential difference. Think of it as the electrical push or pressure. And crucially, you connect it in parallel, like across a component to measure the difference before and after.
Okay.
But an ammeter measures the actual flow. How much charge is passing a point per second? So it has to be part of the path. You put it in series right in the circuit, so the current flows directly through it. That's the only way to measure the flow rate. Placement is key.
Got it. So ammeter in the flow, voltmeter across the component.
Precisely.
All right, Q1.3. This one connects light energy and heat. Why wear white clothes on a hot day? The answer is C. White clothes reflect light and absorb less heat. Feels intuitive, but what's the physics?
It's actually really neat physics. Visible light is electromagnetic radiation, and it carries energy. Now, black surfaces are great at absorbing almost all the wavelengths of light that hit them.
They soak it all up.
Pretty much. And they convert that light energy very efficiently into thermal energy heat, which makes you feel hotter.
Makes sense.
White surfaces, though, do the opposite. They reflect most of the light wavelengths back out into the environment. So much less light energy gets converted into heat absorbed by the fabric, keeps you cooler. It's all about how efficiently different colors absorb or reflect that incoming light energy.
Cool. Literally. Okay, let's unpack question 2. This jumps into something that seems simple, but is actually, higher order thinking. Electrostatics. Specifically, that charged plastic ruler near a neutral piece of tissue paper.
Yeah, this is like the textbook demonstration of charging by induction.
Yeah.
So you rub the ruler, it picks up extra electrons, making it strongly negatively charged. We start there.
Okay, ruler's negative. Q2.1 asks, what do you see when this negative ruler gets close to the neutral paper?
The observation is simple. The paper is attracted towards the ruler. Or, it might even stick right to it.
Simple observation, but the explanation. Q2.2, that's the tricky part, right? This is where the high flyers show their understanding. If the paper is neutral, why is it attracted? Don't only opposite charges attract?
Exactly the right question to ask.
Yeah.
This is all about charge redistribution, or what we sometimes call temporary polarization. So that strongly negative ruler comes close, and it exerts a force on the electrons within the neutral tissue paper. Remember, atoms have positive nuclei and negative electrons, and in many materials, some electrons can move a bit.
Okay.
Since, charges repels negative Terry. The electrons in the paper that are free to move get momentarily pushed away from the ruler. They shift toward the far side of the piece of paper.
Ah, okay. So the negative charges kind of scoot over to the other side?
That's a good way to think about it. They scoot away. And if those negative charges move away from the side closest to the ruler, what's left behind on that near side?
The positive bits. The nuclei.
Exactly. That side now has a temporary shortage of electrons, exposing the positive charge of the nuclei. So the side of the paper nearest the ruler becomes temporarily positively charged.
So it's not that the whole paper becomes positive, just one side of it.
Precisely. The paper overall is still neutral. It has the same total number of protons and electrons, but the charge is now separated, polarized. You've got your strong negative ruler right next to this temporarily positive patch on the paper. And what do opposite charges do?
They attract. So the paper moves towards the ruler.
There you go. That's induction. The negative ruler induced a temporary positive charge separation in the neutral object, leading to attraction. It shows how powerful that electromagnetic force is, even without direct contact.
Okay, moving on. Question 3 takes us into current electricity, the flow, starting with the nuts and bolts circuit construction. Q3.1 asks you to draw a circuit diagram. 2 cells in series, 2 bulbs in series, and a switch.
Yeah, drawing skills are super important in science. You got to communicate clearly. And for marks here, you need to hit 4 specific points. First, those 2 cells, the batteries, they need the right symbol and must be connected in series. That means positive terminal of one connected to the negative of the next.
Okay, series connection for cells. What else?
Second and third, the 2 light bulbs. Standard symbol, that circle with an X inside. And they also have to be in series. That means one after the other, forming a single, unbroken path for the current.
One path. Got it. And the 4th point?
The switch. Got to include the switch symbol, and it can be shown either open or closed. Doesn't matter for the drawing mark itself, as long as it's there and drawn correctly.
All right. So once you've built that circuit correctly, Q3.2 asks what happens when you close the switch. Seems straightforward.
Yep. Close the switch, complete the path, and the bulbs will light up. Current flows.
Now, Q3.3. This is where the real analysis of series circuits comes in. You add a 3rd light bulb, also in series. Q3.3.1 asks for the observation, what do you see happen to the bulbs?
Visually, the result is clear. The brightness will decrease. All the bulbs will get dimmer.
And Q3.3.2 asks why. This is the core concept, right? Why do they dim when you add more stuff in series?
The fundamental reason is that the total resistance of the circuit increases.
Right. I think sometimes students find that counterintuitive, like you're adding another bulb, shouldn't that, do more? But it actually makes the whole system perform worse in a way. Can we use that water pipe analogy?
Absolutely. The analogy works great here. Imagine the electric current is like water flowing through a single pipe. Each light bulb acts like an obstacle, maybe a narrow section or a kink in that pipe, resisting the flow.
No way.
When you add a 3rd bulb in series, you're essentially adding a 3rd kink into that same single pipe. So the total opposition to the water flow, the total resistance, it just adds up. It increases.
More obstacles in the one path.
Exactly. Now, the push from the power source, the voltage, that stays the same. But because the total resistance is higher, the overall rate of flow, the current, must decrease. Think Ohm's law. Less current flows through the entire circuit.
And since less current flows through all the bulbs,
less energy gets delivered to each bulb per second. Lower power output means dimmer light. That reduced current flows equally through all 3, so they all dim together.
Okay, so the key things for series are resistance adds up, current's the same everywhere, but decreases overall if you add more stuff, and voltage gets shared or dropped across each component.
You got it. And that single path idea is crucial. If you break the circuit anywhere, like one bulb burns out, the whole thing stops working. Remember those frustrating old Christmas lights?
Definitely. Okay, Q3.4 changes topic slightly. Still about current, but focuses on the energy transformation, specifically the heating effect you see in things like kettles, toasters, hair dryers.
Right, so Q3.4.1 just asks you to identify this effect. It's the heating effect. Simple enough?
And Q3.4.2 asks for the energy conversion. What's turning into what?
It's electrical energy being transformed primarily into heat, or thermal energy.
Okay, but again, for the students really aiming high, Q3.4.3 wants the mechanism. Why does heat get generated when current flows through certain wires?
It boils down to resistance again, but really at the atomic level this time. Those appliances designed specifically to get hot, like a stove element or the coil in a toaster, use special wires, often made of an alloy like nichrome, and nichrome has very high electrical resistivity.
So it's deliberately chosen to be bad at conducting electricity.
In a sense, yes. It deliberately resists the flow of electrons much more than, say, a copper wire. When the electrons are forced by the voltage to push through this high-resistance material, they are constantly colliding with the atoms that make up the wire structure.
It's like microscopic friction, or a really crowded hallway. The electrons keep bumping into things.
That's a perfect analogy. Constant collisions. Each collision transfers kinetic energy from the moving electron to the atom it hits. This makes the atoms vibrate much more rapidly and intensely.
And that vibration is heat.
Exactly. That increased atomic vibration is what we perceive as heat, thermal energy. If you push enough current through it, enough collisions happen, enough heat is generated, the wire gets so hot it starts to glow, usually red or orange. That means some of that thermal energy is now being converted into light energy too. We call that incandescence. But the core process is resistance, causing collisions, transferring electrical energy into thermal energy.
All right, let's make that crucial comparison now. We've done a series. Now, question 4 moves us to the other main type, the parallel circuit.
Yes, and understand the difference is key. Q4.1 asks for the type of circuit shown, and Q4.2 asks why. It's clearly a parallel circuit, and the reason, because the electric current has multiple paths to flow through.
So if the series circuit was that single pipe with kinks, the parallel circuit is like the main pipe splitting into several separate branches.
Precisely. The current reaches a junction and it splits. Some goes down one path, some down another. It has options.
And that completely changes the behavior, doesn't it? Which we see in Q4.3, looking at this learner's experiment comparing brightness. Circuit A has 2 bulbs in parallel. Circuit B adds a third bulb also in parallel.
Right. Q4.3.1 is just observation. Circuit B has 3 bulbs. Easy mark.
But Q4.3.2 is the comparison. How does the brightness of the bulbs in Circuit B with 3 compare to Circuit A with 2? The memo says the brightness will be similar or maybe even brighter. Now, that's different from series.
Totally different. And this is often a sticking point. Why don't they get dimmer like in series? Why might they even get brighter? This seems weird after what we just discussed.
Yeah, what's going on there?
The absolute key difference is voltage. In a parallel circuit, each branch, each path, is connected directly across the terminals of the power source. This means each bulb receives the full voltage supplied by the battery.
Ah, so they're not sharing the voltage like in series.
No sharing. Each one gets the full push. And since the power output of a bulb, which determines its brightness, depends heavily on the voltage across it specifically, voltage squared in the power formula, if the voltage stays high, the brightness stays high. So adding another bulb in parallel doesn't reduce the voltage across the other bulbs. They stay bright.
Okay, that explains similar. But what about brighter? How could adding a bulb make things brighter?
Okay, this dives a bit deeper and relates back to resistance, but in the opposite way to series. When you add another path for the current to flow that third bulb in its own branch, you actually decrease the overall total resistance of the entire circuit.
Wait, adding something decreases resistance? That sounds backwards.
It does sound counterintuitive. But think about it like opening another checkout lane at a busy supermarket. More lanes open means less overall blockage, easier flow for everyone. Adding another parallel path makes it easier for the current to leave the battery.
Okay, I think I get that. More pathways means less overall opposition.
Exactly. And if the total resistance of the circuit goes down, what happens to the total current drawn from the battery, assuming the voltage stays the same?
Ohm's law again. Lower resistance means higher current.
Bingo. The total current flowing out of the battery actually increases quite a bit. Now, while the individual bulbs mostly stay the same brightness because they get full voltage, sometimes with real batteries that have internal resistance, providing an easier path, lower total external resistance, allows the battery to maintain its voltage more effectively or push out that higher total current more easily. This can sometimes lead to a slight increase in brightness, hence the brighter possibility.
Wow, okay. That's a much more detailed picture than just they stay the same.
It is. But the main takeaway for parallel circuits is voltage across each branch is the same and equal to the source. Current splits at the junctions, with the total current increasing as you add more branches. And crucially, total resistance decreases as you add more branches. It's the inverse of series.
Got it. Okay, Q4.3.3 tests a different skill, formulating an investigative question based on this setup. What makes a good question here?
A good scientific question has to be testable, and it needs to clearly link the independent variable, what you change, to the dependent variable, what you measure. Here, the independent variable is the number of bulbs added in parallel.
Right.
So a good question might be, how does increasing the number of light bulbs connected in parallel affect the total current drawn from the battery? Or, what is the relationship between the number of parallel branches and the total resistance of the circuit? Or even, does the brightness of an individual bulb change when more bulbs are added in parallel? It needs to be specific and suggest what you're measuring.
Okay, clear link between variables. And finally, Q4.3.4 asks for the conclusion from this kind of investigation.
Based on the physics, the conclusion should state something like, adding light bulbs in parallel causes no significant change in the brightness of the individual light bulbs, because they still get the full voltage. Or, for a more advanced answer, adding light bulbs in parallel decreases the total resistance of the circuit and increases the total current supplied by the source.
Focusing on that decrease in total resistance is really the key differentiator for parallel, isn't it?
Absolutely. Master that difference between how resistance behaves in series versus parallel, and you've mastered a huge chunk of circuit theory.
Okay, switching gears one last time within Section A. We're moving away from circuits now and into light and optics with question 5. This one's all about how we see color.
Right. We've got this scenario. Someone's wearing a shirt and shorts. We look at them under different colored lights. First, under red light. The shirt looks red, but the shorts look black.
Okay.
Then under blue light. This time the shirt looks black and the shorts look blue.
So Q5.1 and Q5.2 ask us to figure out the actual colors of the clothes if you saw them in normal daylight. Based on that info. The shirt must be red, right? Because it looked red under red light.
Correct. It reflected the red light.
And the shorts. They looked blue under blue light, so they must actually be blue.
Exactly. Shorts are blue.
Now, Q5.3 wants the explanation. Like, why did the blue shorts appear black when seen under the red light?
This tests the fundamental idea of color perception. An object appears a certain color because it reflects that color of light and absorbs others. The blue shorts are blue because they reflect blue light well and absorb other colors, like red and green.
So under red light?
Under red light, the blue material absorbs essentially all the red light that hits it. Since it reflects almost no light back to your eyes, it appears black. Black is basically the absence of reflected light.
Makes sense. So Q5.4 asks, how could you see the true colors of both the red shirt and the blue shorts at the same time?
You need a light source that actually contains both red and blue light, and ideally all the other colors too, for them to reflect. That means you need white light. Think sunlight or a standard white light bulb. White light is a mixture of all the colors of the visible spectrum.
Got it. White light reveals true colors. Okay, so let's push this concept. Q5.5. What would you see if you shone pure green light on this person wearing the red shirt and blue shorts?
Okay, think about absorption again. The shirt is red, meaning it absorbs green light very well. The shorts are blue, meaning they also absorb green light very well. Neither garment is good at reflecting green.
So, if they both absorb the green light and reflect none of it,
then both the red shirt and the blue shorts would appear black under pure green light. Perfect test of understanding absorption and reflection.
Cool. All right, Q5.6 changes focus slightly, moving to just the basic behavior of light hitting a surface, reflection. First, Q5.6.1 asks for a definition.
Okay, a good definition of reflection is when light bounces off a surface and changes direction, but stays within the same medium.
Right, staying in the same medium is important. It's not passing through and bending like.
Exactly. That's refraction, where light crosses a boundary into a new medium, like air to water or air to glass, and then changes direction. Reflection is a bounce, refraction is a bend as it goes through. Big difference.
Okay. And Q5.6.2 involves labeling a diagram showing reflection. This diagram illustrates the law of reflection, right? What are the labels?
Yes, it's fundamental. You need to identify 4 parts correctly. A is the normal. It's an imaginary line drawn perpendicular at 90 degrees to the reflecting surface right at the point where the light ray hits. It's our reference line for measuring angles.
Okay, the perpendicular reference line.
B is the angle of incidence. This is the angle measured between the incoming light ray, the incident ray, and the normal.
Between incoming ray and normal. Got it.
C is the angle of reflection. This is the angle measured between the outgoing reflected light ray and the normal.
Between outgoing ray and normal.
And finally, D is simply the reflected ray itself, the light ray bouncing off the surface.
So the crucial law this diagram shows, the thing every student needs to know is...
The law of reflection.
Yeah.
The angle of incidence, B, is always equal to the angle of reflection, C. Angle B, angle C. This simple law governs how mirrors work, how light bounces off surfaces, and it's essential for designing things like telescopes and periscopes.
Perfect. Angle in equals angle out, measured from the normal. And that wraps up our really deep dive into Section A, energy and change. We've hit electrostatics, series circuits, parallel circuits, heating effect, color, reflection. A lot of ground covered.
Definitely.
Okay, let's take a quick mental breath here, because now we are shifting scale dramatically. We're moving from electrons and light waves to the entire cosmos. Get ready for Section B, Earth and beyond, astronomy time.
All right, Section B, kicking off with some astronomy fundamentals in question 6. Q6.1 asks for the second closest gas planet to the sun. You got to know the order.
Okay, so the gas giants start after the asteroid belt. Jupiter is the first one, so the second one must be Saturn, C.
Correct. Jupiter, then Saturn.
Q6.3 asks about the age of our sun. This feels like a key number in cosmic history.
It really is. The sun is estimated to be 4.6 billion years old.
Yeah.
And just for context, that makes it roughly middle-aged.
Really? Only halfway through?
Pretty much. It's expected to continue burning hydrogen in its main sequence phase for about another 5 billion years before things start to change dramatically and it expands into a red giant. So we're in a good stable period right now.
4.6 billion years. Wow. Okay, Q6.2 mixes in a bit of physics calculation. It asks for the distance between the Earth and the Moon. It tells us light takes 1.28 seconds to travel that distance, and the speed of light is 300,000 kilometers per second.
Yeah, nice little application of the basic distance speed acts time formula.
So you just multiply the speed by the time. 300,000 kilometers multiplied by 1.28 seconds.
Huh.
Let's see, that comes out to 384,000 kilometers, which is answer B.
Spot on. 384,000 kilometers. And it's a good reminder of just how vast space is. Even our closest celestial neighbor is over a light second away. Light isn't instantaneous across those distances.
True. Okay, question 7 digs a bit deeper into the solar system's structure and energy. Q7.1 asks for the general shape of our solar system.
The accepted descriptions are generally disc-shaped, or maybe circular. Some might even say spiral-shaped, thinking about the galaxy. But disc-shaped is probably best for the solar system itself. All the planets orbit the sun roughly in the same flat plane called the ecliptic plane. So the whole arrangement is relatively flat, like a disc.
Okay, disc-shaped. Q7.2 is a bit of planetary trivia. Which planet has 68 moons? That's a lot.
That huge number belongs to the king of the planets, Jupiter.
68? Why does it have so many?
It basically comes down to its enormous size and gravity. Jupiter's mass is more than twice the mass of all the other planets combined.
Whoa.
Yeah, so its gravitational pull is just immense. It acts like a giant cosmic vacuum cleaner, gravitationally capturing asteroids and other smaller bodies that stray too close. Over billions of years, it's collected this huge family of dozens and dozens of captured moons or satellites.
A gravitational powerhouse. Okay. Q7.3 gets to the heart of it all. What is the source of the sun's energy?
The engine driving the sun, and therefore our entire solar system, is nuclear fusion reactions happening deep within its core.
Nuclear fusion. Can you unpack that a little? It sounds pretty intense.
It is incredibly intense.
Yeah.
Deep in the sun's core, the pressure from its own gravity is immense, and the temperature is millions of degrees Celsius. It's so hot and dense that hydrogen atoms are stripped of their electrons, forming a state of matter called plasma.
Okay.
Under this extreme pressure and heat, the nuclei of hydrogen atoms, which are just single protons, are forced to overcome their natural electrical repulsion and slam together, fusing to form helium nuclei. Primarily, 4 hydrogen nuclei fuse into one helium nucleus through a couple of steps.
And that fusion releases energy.
A tremendous amount. During this fusion process, a tiny fraction of the mass of the original hydrogen nuclei doesn't end up in the final helium nucleus. It gets converted directly into pure energy, according to Einstein's famous equation, EMC/Fc. Mass becomes energy. And it's this continuous conversion of mass to energy in the core that radiates outwards as light and heat, powering the sun and sustaining life on Earth.
Mind-blowing stuff. Okay, now for Q7.4, this feels like a really important one, especially for understanding our own planet. You needed to list and describe 2 specific factors that make life, as we know it, possible on Earth.
Yeah, this is fundamental. The first, and arguably the most critical factor, is our distance away from the sun. Earth orbits within a region astronomers call the habitable zone, or sometimes the Goldilocks zone.
Not too hot, not too cold.
Exactly, just right. This specific distance means the average surface temperatures on Earth allow water to exist primarily in its liquid form. Liquid water is considered absolutely essential for the chemistry of life as we know it.
So if we were closer, like Venus.
Too hot. Any water would likely boil away, leading to a runaway greenhouse effect like Venus has. If we were further out, like Mars.
Too cold, water freezes solid.
Right. Mars has ice, but very little, if any, stable liquid water on its surface today. Our just right distance allows water to exist here in all 3 phases: solid ice, liquid water, and gaseous water vapor, which drives weather and is vital for biology.
Okay, so distance allowing liquid water is number 1. What's another key factor?
The second indispensable factor is the sunlight itself. Not just the heat, but the light energy.
For plants.
Primarily, yes. Photosynthetic organisms, plants on land, phytoplankton, and algae in the oceans capture the energy in sunlight and use it, along with carbon dioxide and water, to produce their own food, sugars, through the process of photosynthesis.
And that forms the base of the food chain.
Completely. That conversion of light energy into chemical energy is the primary source of energy for almost all ecosystems on Earth. Without sunlight driving photosynthesis, the vast majority of food webs would collapse. So distance for liquid water and sunlight for energy production via photosynthesis, those are probably the top 2. You could also mention our atmosphere having oxygen or having a magnetic field for protection, but distance and sunlight are core.
Great explanation. Okay, Q7.5 looks at that table provided, showing data for the first 4 planets: Mercury, Venus, Earth, Mars. Q7.5.1 asks what these 4 planets have in common.
Looking at them, they are the inner planets, the ones closest to the sun. Their key shared characteristic is that they are all rocky planets, also called terrestrial planets. They have solid, dense surfaces you could theoretically stand on, unlike the gas giants further out.
Right, solid ground. And Q7.5.2 asks us to use the table data, specifically the diameters, to identify the largest planet among these 4.
Okay, just got to scan the diameter column in the table. Mercury is small, Venus and Earth are similar, Mars is smaller again. Earth's diameter is listed as 12,756 kilometers, which is the largest value in that group. So the answer is Earth, supported by the diameter data.
Okay, let's zoom out even further now. We've looked at our solar system. Question 8 takes us up to the scale of galaxies. Q8.1 starts with the definition. What is a galaxy?
Right, stepping up the scale. A galaxy is essentially a massive, gravitationally bound system consisting of billions of stars, stellar remnants, interstellar gas, dust, and dark matter. The key part is gravitationally bound. Gravity is the cosmic glue holding these immense structures together.
Billions of stars. Hard to even imagine. Okay, Q8.2 is a bit of cosmic trivia again. Why do we call our galaxy the Milky Way?
That name comes from its appearance in the night sky from Earth. On a really clear, dark night, away from city lights, you can see this faint, hazy, whitish band stretching across the sky. Ancient observers thought it looked like a smear or spill of milk, and the name stuck.
Like spilt milk across the heavens. Cool. Okay, now Q8.3. This is crucial for understanding scale. What's the difference between a galaxy and the universe?
This really tests your grasp of cosmic hierarchy. A galaxy like our Milky Way or the nearby Andromeda Galaxy is already enormous, containing, as we said, hundreds of billions of stars, spanning maybe 100,000 light years across. It's a single vast island of stars and gas and space.
An island. Okay, so the universe is?
The universe is, well, everything. It is the entirety of space and time and all the matter and energy within it. The universe contains all the galaxies. Current estimates suggest there might be hundreds of billions, maybe even trillions of galaxies in the observable universe.
Whoa.
Yeah. So a galaxy is just one component, one island within the vast, perhaps infinite ocean that is the universe. The scale difference is almost incomprehensible. Galaxy island. Universe, the entire ocean containing all the islands and all the space between them.
Okay, that clarifies the scale. Universe is the absolute biggest thing. And Q8.4 asks, where are we located within our own galaxy, the Milky Way?
We're not in the center. Thankfully, it's probably quite chaotic there with a supermassive black hole. Our sun, and our solar system with it, is located in one of the Milky Way's spiral arms specifically, a smaller spur called the Orion Arm, or Orion Cygnus Arm. And we're situated roughly 2/3 the way out from the galactic center, towards the edge.
So kind of in the galactic suburbs.
That's a great way to put it. Relatively quiet out here in the suburbs of the Milky Way. All right, Question 9 wraps things up by looking at the history of astronomy and the tools we use to study the cosmos today.
Q 9.1 takes us way back. Before we had clocks and calendars like today, what did ancient civilizations use the regular movements of the stars and planets for?
Primarily, they used these predictable celestial cycles, the daily movement of the sun, the monthly phases of the moon, the annual journey of the sun through the constellations, the wanderings of the planets to mark the passage of time. This was essential for developing the first calendars.
Calendars for farming and stuff.
Exactly. Knowing when to plant crops, when to harvest, predicting seasonal changes like floods or monsoons, and also for scheduling religious ceremonies and festivals, the sky was humanity's first reliable clock and calendar.
Makes sense. Q 9.2 is a straightforward definition. What do we call a person who studies stars and other objects in space?
That person is an astronomer.
Okay. Now, Q 9.3 focuses on something closer to home for South African students. SALT. What does the acronym SALT stand for?
SALT stands for the South African Large Telescope. It's a major international observatory, and yes, it's located near the town of Sutherland in the Northern Cape Province.
Why Sutherland? Is there a reason it's there?
Yeah, the location was chosen very carefully. Sutherland is high up on a plateau, the air is very dry, and crucially, it experiences very little light pollution from cities. These conditions, high altitude, dry air, dark skies, are ideal for astronomical observations, especially for optical telescopes like SALT.
Which leads right into Q 9.4. What is an optical telescope? What defines it?
An optical telescope is, quite simply, a telescope designed to collect and focus electromagnetic radiation, primarily in the visible light part of the spectrum, the light that our own eyes can see. It does this using a system of lenses, in refracting telescopes, or mirrors, in reflecting telescopes, or sometimes a combination, to gather faint light from distant objects and magnify the image. SALT is a large reflecting telescope.
Okay, so it works with the light we can see, using lenses or mirrors. And the final question, Q 9.5, asks for the name of probably the most famous optical telescope currently orbiting Earth. It's named after the astronomer Edwin Hubble.
That would be the one and only Hubble Space Telescope.
Hubble. And Edwin Hubble himself was pretty important, wasn't he?
Hugely important. Edwin Hubble was the American astronomer who, back in the 1920s, made groundbreaking observations showing that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This was the first strong evidence for the expansion of the universe, completely changing our understanding of cosmology.
Wow. And the telescope named after him, why is putting it in space such a big deal?
Being in orbit above Earth's atmosphere is its huge advantage. Our atmosphere, while essential for life, actually blurs and distorts incoming starlight. Twinkling is caused by this. It also blocks certain wavelengths of light. By being in space, Hubble avoids all that atmospheric interference.
So it gets a much clearer view.
Incredibly clear. It allows Hubble to capture extremely sharp, detailed images, and to see much fainter and more distant objects than most ground-based optical telescopes could at the time it was launched. It's given us breathtaking views of everything from nearby planets to the most distant galaxies in the early universe.
What a journey from ancient people looking up to mark seasons to having telescopes in orbit peering back billions of years.
It's an amazing progression of human curiosity and ingenuity. Hashtag tag outro.
And we did it. That's a full deep dive through the entire Grade 8 Natural Sciences pre-examination paper and memo.
Yeah. We covered a lot of ground.
Absolutely. We went from, the tiny push and pull of electrons causing static cling, through circuits, understanding why resistors get hot, how parallel paths change everything,
To figuring out why clothes look different colors under different lights, how reflection works.
and then zoomed all the way out to planets, stars, the sheer scale of galaxies and the universe, and how we even study it all. You should now have the facts, yeah, but also the explanations, the context behind them.
Hopefully, yeah. And that context, that connection is really the most important thing to take away, I think, if we link it all back. Whether you're looking at why resistance causes heat in a wire, or why Earth is habitable, or how gravity holds a galaxy together.
It's always about connecting the what to the why.
Exactly. Connecting the observation, the fact, the definition, the what, to the underlying scientific principle, the physics, the mechanism, the why. That's critical thinking in science.
Understanding why adding a parallel path makes the total resistance go down, not up, or why the angle of incidence equals the angle of reflection, or why that specific distance from the sun is so crucial for liquid water. Applying those core principles, that's the knowledge that really sticks.
That's the real goal, beyond just the exam. That ability to apply principles is what defines real scientific understanding, what makes a high flyer. So keep practicing that kind of thinking.
Definitely. Keep asking why. Okay, so to leave you all with a final thought, something to maybe chew on as you study, we talked about astronomy, right? We learned our sun is 4.6 billion years old, powered by nuclear fusion, converting mass to energy. We learned the universe contains maybe trillions of galaxies.
Right.
But here's something astronomers grapple with. When they measure how galaxies spin or how galaxies move in clusters, they find there isn't nearly enough visible matter, stars, gas, dust to provide the gravity needed to hold them together the way they observe. It seems like they should fly apart.
The missing mass problem.
Exactly, which leads to the idea of dark matter, some invisible stuff providing extra gravity, and dark energy, some mysterious force accelerating the expansion of the universe. So the provocative thought is this. What unseen energy conversions, what fundamental processes involving this dark matter and dark energy might be happening out there across billions of light years, processes that are essential for the structure and fate of the entire cosmos, but that we currently have almost no understanding of? What physics are we totally missing?
That's a big question for the next generation of scientists. It highlights how much we still have to discover.
Definitely something to mull over.
For now, though, focus on mastering what we do know for this exam. We really wish you all the very best of luck with your preparation.
Yeah, absolutely. Keep diving deep into your studies, use this session however helps you best, and keep that scientific curiosity burning. Good luck, everyone.